So, after volume fraction, let us look at surface area per unit volume estimation. Let us consider a polycrystalline microstructure. Something like this, an illustrative sketch for a polycrystalline single phase microstructure. These are grain boundaries, the lines, and in the 3-dimensional structure it is surfaces. Now, if I superimpose on this, let me superimpose on this a grid of lines. I count the number of intersections that these lines make with the grain boundaries. Just like in the case of graphite nodules, you had measured the intersections with the graphite boundaries. These are all intersections that you need to count. And if this is n, is the number of intersections, the total length of the lines, of all the lines added together is, let us say, capital L, then n upon L gives you the number of intersections per unit length, which you estimated in the graphite nodule microstructure. That was simply, the relationship was simply written that the total boundary length of these lines per unit area. Okay. So, this is the total boundary length per unit area is given by this relation. Now, we will see how we get this particular relationship. Let us take these line grid and the distance between the line grid is, let us say, t. Okay. Now, let me do one more thing, divide these grain boundaries in this structure into small infinitesimal elements d lambda. Okay. And let there be total of m such elements. Then the total length of grain boundaries inside this would be m times d lambda. Okay. This is the way I have just subdivided all the entire network of boundaries into these small elements. So, m times d lambda is clearly the total length. Now, these grain boundaries are completely randomly oriented. This is the assumption that we need to make here, which means that each of these element d lambda behaves like a Buffon's needle. Okay. Each of these grain boundary segment of infinitesimal length d lambda behaves like a Buffon needle that we have simply thrown on this line grid. What is the probability that a particular segment will intersect one of these lines? That we have already seen is 2 times d lambda upon pi t. Number of expected number of intersections small n that I should get would be this probability multiplied by m needles. So, this would become 2 by pi, I will introduce m times d lambda upon t. Now, m times d lambda is simply L. Okay, this is the expected number of intersections. Now, I want to divide, okay, this will get confused here. Let me call this as n L sub b to represent that these are boundaries. So, here also it will be L sub b. Now, what is the total length? What is the total length? PL is simply small n upon the total length of these horizontal lines, the line grid. Let me also show here that the dimensions of my microstructure, this is L, this is L, small l. So, what would be the total length if I have a set of parallel lines spaced t apart along the length L? This total length L would be L square upon t. Okay, L upon t will give you number of lines. Each line is of length L, hence it becomes L square upon t. Okay, number of lines is L upon t, each line is of length L, so it becomes L square upon t, which means that here also on the right hand side also I divide by the total length. So, 2 by pi L b times t, and I divide by L square upon t. Now, this t and this t will cancel, this will become 2 by pi L b upon L square. What is this quantity? L b upon L square. L b is the total length of grain boundaries divided by the area over which it is present. So, therefore, this is nothing but boundary length per unit area. So, if I now look at this, it is clear that boundary length per unit area is equal to pi by 2 times. So, we arrive at this relationship. Okay. So, this was a simple derivation to show this one of these stereological relationships. Now, we go to 3 dimensions, because I am interested in the surface area per unit volume. Okay. This was an exercise in 2 dimensions. Let us do an exercise in 3 dimensions. The exercise in 3 dimensions, I have now surfaces. Okay. Surfaces can be in the form of particles, it can be in the form of grains, it does not matter. These are all my surfaces. Just like I had divided the lines into small infinitesimal elements, I divide the surfaces also into small infinitesimal areas. Each of them having an area ds. Okay. and these area elements are randomly oriented and randomly distributed in the 3-dimensional structure or within the cubic space. Now, I introduce a line probe parallel to the z axis, but positioned randomly. What is the probability that this line probe will intersect any one of these surface elements? Imagine that you have just one such element which is having some orientation of theta with the z axis and its projection having an angle of phi with the x axis. This is my orientation of this one particular any one element of area ds. It will project an area on the xy plane dsp, projected area. This projected area dsp is going to be equal to is going to be some function of theta and ds. Is going to be now what is that going to be? What would be the projected area of a small infinitesimal element onto the xy plane whose orientations is theta and phi? This is going to be dsp would be equal to ds cosine theta. You can see this when theta is 0, this element is aligned perpendicular to the z axis. It will get projected as ds and cos theta will be 1. If it is theta is 90 degrees, then it will project as a line which has 0 area. So, when put theta is equal to pi by 2, it gives you 0, and it is going to be independent of phi. So, you can rotate this, you will get the same. Now, what I need is the average projected area. Then only I can calculate what is the probability that a line probe will intersect this element. What is the average projected area? Well, by now we know this, and I am going to write this. ds will be taken out of the integral 4 pi cos theta, and then sin theta is coming from the probability density function of orientations in 3D space, and 4 pi is also coming from there, sin theta upon 4 pi, d phi d theta. Phi varies from 0 to 2 pi, theta varies from 0 to pi. Now, I think by this time I am sure you would be able to solve this integral. First integrate with respect to phi, you will get 2 pi, which will cancel with 4 pi. You do not need to integrate all the way from 0 to pi, you can integrate from 0 to pi by 2, so factor of 2 will come, and you just have to integrate this cos theta sin theta term, which is a straightforward integral, and the result I am writing directly is ds upon 2. Okay. This is the result. So, probability of intersection, if I call that as P, intersection with a line probe, is the average projected area dsp upon the area of the face in the xy plane. So, L square, or this is simply ds upon L square, and there is a factor of half that would be there. If there are total of m such small infinitesimal areas of the surfaces, then the number of intersections small n, the expected number, is going to be is going to be p times m, the probability times the number of such elements that are there, which is m times ds upon L square. Now, clearly m times ds is nothing but the total surface area inside this cubic block. So, let us call that as just S upon L square. Now, divide both sides by L. If I divide the left hand side by L, I will get PL, number of intersections per unit length. So, PL is equal to small n upon L, which is equal to half times S divided by L cube. Both sides I have divided. S upon L cube is nothing but surface area per unit volume. Hence, surface area per unit volume would be 2 times PL. Okay, so we have now a relationship that if I take a microstructure, let us say a polycrystalline microstructure or particle microstructure, it does not matter, I get PL out of this, 2 times that is simply an estimate of the surface area of the grain boundaries in a unit volume. And remember that boundary length per unit area of this was pi by 2 PL. This we had already seen, which means that I can relate SV and BA as well, and I can write SV to be equal to 4 upon pi BA. Okay. That if I have so many boundary lengths in a unit area, multiply this by a factor of 4 upon pi, I will get so much of surface density in the material. Okay, so we have done surface area per unit volume. Now I want to do length density or length per unit volume. Or the parameter L sub v. So, that was a third parameter that we want to get a stereological relationship for, and this you will see is going to be very easy, and we will be following the same line of reasoning. Again, we just restrict ourselves to cubic space. So, I have full of linear elements inside my 3-dimensional structure, all randomly oriented. If I take a section through this, then on this section I should be able to see points. So, I should be in my microstructure be able to isolate points in the structure. And let us see what I can do with these points and how, looking at this structure, I get at length per unit volume. We will do exactly the same thing, just divide these, all of these line elements into small infinitesimal elements. Again, let me call that as d lambda only, and there are m such elements, and hence the total length of lines inside the cube, let that be capital L, is nothing but m times d lambda. So, we start with the same thing, that this section will cut some of these small d lambda elements. What is the probability of a d lambda element intersecting a plane probe? Probability of d lambda element intersecting a plane probe. It should be the mean tangent diameter of the d lambda of one element divided by L, simply. We have already seen this, that a plane probe intersects a feature, then one has to look at the mean tangent diameter. What is the mean tangent diameter of such an element? That we saw in the last lecture. We derived a relationship for a cylinder, and then we let the radius of the cylinder go to 0, then it becomes a line, and hence the mean tangent diameter for that would be the length of that element divided by 2. So, this is simply d lambda by 2 divided by L. Number of points. So, n, number of points expected in the structure, in the two dimensional structure would be, there are total of m such elements, and hence m times this probability should be the expected value of the number of intersections. So, this would be m d lambda upon L, and there is a factor of half. Now, what I measure, remember I said that we measure basically ratios of two quantities. So, I actually would measure number of points per unit area, P sub A. So, P sub A would be n divided by area of my section, and area of my section is L square. So, this is half m times d lambda is the total length of the elements, and I have also I have to divide by L square. So, this will become L cube. So, this capital L upon L cube is the total length divided by the volume of the cube. Hence, this is nothing but length per unit volume. So, from here length per unit volume is 2 times the number of points per unit area. So, now I have related PA here, points per unit area, on the slide you can see is related to length per unit volume. Now, I have the last fundamental relationship left in stereology, which is number per unit volume. When I have so many particles in a unit volume, how can I estimate that? So, numerical density NV, number of particles per unit volume. So, I have again particles or precipitates inside, and there is some number per unit volume of such particles that I need to estimate. When I take a section through this, I get these section profiles of these particles, and here I can measure Na, number of particles per unit area. What is the relationship between Na and Nv? Let us assume that all my particles in this, so all particles here have same size and shape, which means that they will all have same value of the mean tangent diameter, okay? Which means that this section, the probability of intersecting a particle by the two dimensional probe would be h bar upon L. Well, L again is my dimension of the cubic space. In this space, let us say I have capital N number of particles, and out here I have small n number of section profiles. Then the relationship between small n and capital N would clearly be related through this probability, that capital N times the probability would give me an estimate of small n. So, n would become capital N times the probability, which is n times h bar upon L. To get points per unit area, not points, sorry, to get number per unit area on my two dimensional microstructure, I have to divide small n by the area of my image, which is L square. So, n upon L square. Here also I need to divide. So, this would become h bar times n upon L cube. Now, n upon L cube is nothing but number per unit volume. So, this is equal to number per unit volume. Hence, Na is equal to h bar times Nv. Okay, so, this was a fourth fundamental relationship that we have derived here. If you look at, just to summarize what we have done, this is what we have done. This is just a summary of three ways through which we can measure volume fraction, then relationships between surface area per unit volume. Here I have written L sub A, on the board I have written B sub A, boundary per unit area, both are the same quantity. So, L sub A or B sub A are the same. Here length density L sub V is equal to 2 times Pa, and numerical density, which is Na is equal to h bar Nv, which we just now derived. Very quickly, we just look and summarize this as well, that if I have to get volume fraction, get a point count by putting a grid and get a point fraction, and that is your estimate of the volume fraction. That we have done repeatedly, I do not have to stay with it. Now, I have to get surface area per unit volume of this polycrystalline microstructure. One is directly measure all the lengths and get boundary length per unit area, multiply that by 4 upon pi, and that gives you surface area per unit volume, which you just now saw. Or put a grid of lines, count the number of intersections with the boundary, get number of intersections per unit length. You have seen how we can do that, where L is the capital L is the total length of the grid, N is the number of intersections of the line grid with the grain boundaries, and you can calculate the surface density SV as 2 times PL. And also we have seen that boundary length per unit area is pi by 2 times PL. Now, this is a microstructure where I want to estimate length per unit volume, but where are the points in this? If you look at the triple points, these are all triple points. In 3-dimensional structure, these are triple edges. So, you would count each triple point, count all exhaustively, you have to count all the triple points in the structure. I have circled only a few, but you would count all of them in this given area of the microstructure, or you could put a smaller frame in it and count the triple points. So, which you will be shown as demonstration as exercises in the next lecture as to how to do this. Get PA. So, small n is the number of counts of these triple points, divide by the area of the microstructure or area of the frame inside which you have done the counting, and get PA, number of points per unit area, and the linear density then is given by 2 times PA. Okay. Estimation of numerical density. Well, here is the again a very simple relationship. So, if you were to count these particles, you will get NA, but there is a catch in this relationship. All of these relationships, the catch is we do not know h bar, the mean tangent diameter. So, we have 2 unknowns and we are only able to make one measurement. So, it becomes that here, in order to get numerical density number per unit volume, one would have to make some assumptions regarding shape. Once if we can assume that, then we can try to solve this problem. So, out of all those relationships, if we once again look at the summary, all of these relationships have been derived independent of the shape, right. But the last relationship, if you need to solve it, then you would require a knowledge of shape, but all other relationships you do not require a knowledge of shape. I am going to talk about a little bit more on the numerical density, but I think this particular lecture I will stop here, and then we will look at what are called as derived relationships, where out of this we will derive some of the relationships like the particle diameter. If we assume a certain shape, then what kind of numerical density, what is the relationship for the numerical density we can obtain. Then we will also talk about for polycrystalline structure, how we can define grain size and even particle size, and those are the kind of things we will look in the next lecture.